Bueno, él ha tenido las siguientes posiciones: estuvo en el Instituto de Astrofísica de Andalucía, con una beca Ramón y Cajal, todos conocemos bien, en la Universidad de Cambridge como postdoc asociado, y también en la Universidad de Victoria en Canadá como postdoc asociado, y finalmente en el Instituto Max Planck for Astronomy, o para Astronomía en Heidelberg, con una beca postdoctoral también. Él participa actualmente en 3 de los proyectos más grandes que conocemos, son el proyecto Gaia, en el proyecto RAVE y en el SLOAN, en el SDSS, SLOAN Digital Sky Survey, y en CG específicamente como colaborador externo, lo cual habla mucho de, porque aunque no estés en un lugar que haya pagado, te lo están dando por ti, ¿no? Por Jorge Peñarrubia. Bueno, tiene más de 40 pláticas invitadas. Entonces, esto es muy interesante. Más de alrededor, ya vi que el tuyo está, que me mandó una versión bien medio viejita de ya vi los números y los números no son los que tú dices aquí, son más. Tiene más de 50 contribuciones arbitradas con alrededor de 2,000 citas, su número H es 24, o sea, tiene un montón de primer autor. Puedo seguirle, pero mejor tu plática, porque no quiero apenarte ya, ¿no? Entonces, gracias. Bienvenido, Jorge, muchas gracias.
Gracias. Pues, primero, muchas gracias a todos por venir aquí y muchas gracias por invitarme a la UNAM a visitarla. Es mi primera vez en México y la verdad es que ha sido una visita fabulosa. Llevo 5 semanas en el país y espero volver. Entonces, la plática la daré en inglés. Primero porque nunca la he dado casi nunca en español y sería un lío, y segundo porque puede que haya gente que no entienda el español en la audiencia. So, yes, today I'm going to talk about what we really mean when we talk about galaxy masses in an expanding universe. And this is I think it's a timely issue now, because there are many people interested in trying to constrain these quantities all across the universe in different systems, like from galaxy clusters to spiral galaxies to very tiny galaxies, like those dwarf galaxies. And I think it's a concept, the mass of a galaxy, which is very important, and because in this business we are trying to relate things that we can observe, like the properties of the stars, the properties of the gas, with the properties of the galaxy in order to understand how these systems form in the universe. But I hope I can convince you today that the concept of a galaxy mass is not particularly well defined, unfortunately, in cosmology, and on top of that, it's extremely difficult to measure. So it's a bad combination altogether. So the problem really comes when you look at how structures form in an expanding universe. This is, for example, in a pure dark matter simulation, no variance or whatever, where all the things are a little bit more simple than in hydro simulations. And what people find is this kind of result. Here. This kind of result where you have an internal concentration all the way to the virial radius, and I will explain in a second what the virial radius, how this is measured. And then people say, well, all the mass within this spherical volume defined by the virial radius is what we are going to call virial mass, and we are happy with that, and we continue. The problem here really is that the definition of the virial radius comes from a very simple model, which is a top hat spherical collapse model, which basically predicts that the mass within this overdensity, you have a universe that is expanding. You can define on very large scales what is the mean density of that universe. And then you basically put the spherical shells around the center of a structure and measure the mean density all the way out to the point where the overdensity within this radius is 350 times the mean density of the universe, right? And that's what you call the virial radius, and you measure the mass within, and this is the virial mass. It's very simple. It's just the mean density times the volume. And this top hat spherical collapse model predicts that actually all the structures within this overdensity have the same mass, which is not necessarily the case, because the top hat spherical collapse model is a very simple representation. But when you go a little bit beyond this definition and say, okay, let's take a look to the density profile of this substructure. How does it look like? Well, what people find is something like this. You have something like an FW profile, something like the cusp toward the inner regions. As you go out, the density profile goes down to the point where you hit the background density of the universe. The problem here really arises when you look at where is the location of the virial radius of this galaxy. And if you define it as an over density of 350 times, the virial radius will be located here. If you define it as 500, it will be here. If it's 200, as some people do, the virial radius falls in this location. But as you can see, there is nothing special about these radii. There is no feature in the density profile of these dark matter halos that would tell you this is where the virial radius is located. There is no connection whatsoever between the outer, what the universe is doing on very large scales, and the inner distribution of mass in these objects. In other words, the definition of delta, in this case, when we call this is the virial over density, is pretty much arbitrary. And as you can see, well, the fact that people use different deltas in the literature is already hinting in that direction. So there is this interesting paper, very recent, Dimmer and Kravtsov, where they measure the slope, for example, the density profile, and they find something like -1. It will be the density, the cusp, the dark matter cusp, R2 -2. This is where the scale radius of the halo is. And then you can fit an FW, for example, will be this line. So it's a good fit only in the inner regions. Ein Astro profile, which is also pretty common, will be this line here, the dashed line. And the real profile is this thing here, which is steeper than NFW and Ein Astro, especially at outer radii. The problem with this is actually these authors realize that this density profile, the slope, varies very much depending on how fast these halos accrete mass. If they accrete mass mostly at early times in the universe, then they tend to have profiles in the outer radii that are quite steep. Here, the radii are normalized to the virial radius. And if the halos have been forming accreting mass very slowly, then they have basically profiles that are much shallower, something like more looking like Ein Astro. So in principle, there is no evidence that there is a universal density profiles in these systems. Depends on how fast or how slow these halos accreted their masses. So this is quite interesting, and it shows that basically none of the profiles that we are used to provide a particularly good fit in the outer regions. This is a problem, of course, as I said before, because we are trying to use the virial mass as the quantity that tells us how stars form in these halos, right? To relate all these scaling relationships we measure from observational data, we try to tie those relationships as a function of the galaxy or the halo mass of these objects. And there is no clear way how to define the halo mass, then what we are doing, right? What are we doing here? So this is the problem, the first problem. The second problem is that even in our galaxy, for which we have the most detailed data, measuring the virial mass is a big problem. It's very, very difficult. And the reason, of course, is that as you go out, this is just, I'm plotting here velocities versus distances. The virial radius of the Milky Way is supposed to be around 240 kiloparsecs. You can see how the number of tracers, kinematic tracers, starts to become very, very scarce as we go to the outer regions. Right? In the outskirts, we basically don't have tracers that we can really use for measuring the mass of our galaxy, the virial mass. And the problem here is, well, that we have a large number of, a long list of problems here. Is that first, the number drops very quickly. The number of tracers drops very quickly at large radii. But second is that these structures, for example, these tracers do not necessarily be phase mixed, just because the orbital times, as you go out to the virial radius, by definition of the virial radius, become comparable to the age of the universe. That's another way to define the virial radius. It's the radius where the orbital time becomes equal to the age of the universe. So in this volume, the tracers must not necessarily be phase mixed. They didn't have time to phase mix. They are not necessarily spherical, as many people assume. And again, we have no idea whether they are in equilibrium at all. So, sorry for that. And so all these games that people have been playing in the past, which is to assume some tracer distribution, assume equilibrium, a spherical shape, and then extrapolate the mass that you derive in the inner regions all the way out to the outer regions, adopting some kind of density profile, is very dangerous. And this might explain why when people try to measure the virial mass of the Milky Way, they get huge factors, huge discrepancies, much larger than the uncertainties they quote in their papers. And this is, for example, some people that have been trying to play this game in the last few years, and you see the virial mass jumps all the way from basically 0.5 all the way to 3 times 10 to the 12th solar masses. So if you go to AstroPH and you find basically very often papers claiming this is the mass of the Milky Way, well, be aware that this is a very difficult quantity to measure. And worst of it is that the answer very much depends on the tracer you assume, perhaps because we have these kind of issues. Every tracer has their own problems here. All right, so this is one of the fundamental problems of trying to measure the mass of a galaxy using kinematic tracers within those galaxies. Can we do better? Well, I don't know whether this is going to do better, but this is another way to measure the galaxy mass. This is what I'm going to talk today. And it's based on a very basic cosmology. It's a cosmological argument we are going to use in order to measure the mass, what we mean by a mass of a galaxy. And basically, it was an argument that was introduced many years ago by Canal Voltaire in 1957. What these authors did was to say, okay, this is the equation of motion of the universe, of the expansion of the universe, in a universe where all our particles have 0 mass. They are dust particles or tracer particles in an expanding universe. It's the Friedmann equations. But what these authors did was say, okay, you can imagine that the universe now is made of a grid of points, and now these points have their individual masses. So they are not anymore dust particles. Now these points in the grid have a mass. And what these authors tried to find out is what happens to tracer particle galaxies or whatever it is moving around these point masses in our universe, which for us would be like galaxies, right? For us, we would think this is the universe on very large scales. And in this universe, there are galaxies, which we represent as point masses for simplicity. In that case, you can basically modify in a very simple way the Friedmann equations to take into account now that the expansion of the universe is going to be perturbed locally by the fact that these points have now masses. They are not tracers. So basically, space-time around these point masses is going to be perturbed by the mass of these objects. And the modification of the Friedmann equation is now quite trivial. And actually, you see 2 terms. The acceleration, again, of particles moving around these points is going to have an attraction due to the mass of our galaxies, and basically a repulsive term, which arises because we have an omega lambda, a dark energy in our universe. In principle, if you say, I don't want to consider dark energy in my models, what you see is that the motion of particles around galaxies is now Keplerian. So there is no more simple way to characterize the motion of tracer particles around galaxies than this in an expanding universe. Indeed, it's the same. It's the same. You start from the same equation of motion. That's correct. But the way you deal with that, the way you treat those equations of motion is very different. In our case, the objects are already collapsed. And are already collapsed, and we say they are point masses because they are much, we are going to work on scales where all the mass is concentrated, can be concentrated in a point. So we don't have to worry about how the internal mass is distributed in these objects. But yeah, it's very interesting. It's exactly the same equation of motion. Just to illustrate why this is a very simple model for the expansion of the universe locally. This is the equation of motion again. So it's a second-order differential equation. So it's fully specified. The trajectories are fully specified if you tell me what is the position and the velocity at a given time of these particles. So because our initial conditions are very close to the Big Bang, we know what is the relative separation between all the points in the universe. It's very close to 0. So that's going to be our initial condition for R, very close to t equals 0. The Big Bang is going to be 0, R equals 0. The only parameter that we are left with in this equation is the initial velocity. So I'm going to pick some initial velocity. We know it has to be radially positive because that's what the expansion of the universe at the Big Bang is about. Right? The universe was expanding very fast, and that means positive radial velocities. So let's choose one which is not particularly high. If you choose one, the initial velocity, positive, you are very close to R equals 0 at t equals 0, then the particle is going to be moving away from our galaxy. But at some point, because the galaxy has now some mass, you are going to see that this attraction can, in principle, win. And then the particle is going to stop at the apocenter, or turn around radius. That's another way to call it. And then it's going to fall back, just because there is an attraction now. Suponiendo here, we are assuming that our point masses, our galaxies, are isolated from the rest, so that the motion is dominated by the mass of the galaxy. Of course, this is still on very, very small, well, on galactic scales. This is still on megaparsec scales. So the tracer particle around this galaxy will reach a turnaround radius, and then it's going to fall back. It's going to reach a pericenter, and then it's going to move this cyclic motion in and out, okay, forever. Well, not forever, all the way out to the 14 gigayears, the age of the universe in this model, okay? And then we stop here. This is the age of the universe. Now, if you take this position, I'm sorry that you cannot see very well, and instead of R versus time, now you plot radial velocity versus R. So the distance to the galaxy versus the radial velocity of this particle. What you see is that very close to time equals 0, you start very close to R equals 0. The velocity is positive and very high. And then you see as the time goes, and if this particle approaches Apo, the radial velocity becomes very close to 0. This is the turnaround radius. And then it becomes negative. It's falling back. And then you are getting this also. The motion in phase space, this is just the radial section of phase space, is just cyclic again, and it's something like this. So very easy to understand, okay? Now let's play now with initial radial velocity, and let's choose an initial radial velocity that is a little bit higher. Then you get something like this. The initial velocity now is higher, but the particle eventually reaches turnaround radius here and falls back negative positive, and velocity becomes negative. Now you can repeat the game. Higher and higher initial velocities. You do that, and you get this kind of trajectories. Another one, another one, another one. When you sample the initial velocities now, these kind of trajectories, you realize that in phase space, you find how a given structure arises in phase space where all particles will end up on top of this line, the red line, which we call an isochrone. It's only an isochrone because the age of the universe has a finite value. It's 14 gigayears. So the particles in phase space must end up on top of this isochrone in this very simple model. And the interesting bit, and the reason why I started this project, was basically looking at this diagram. This is purely observational data. It's just the radial velocity of galaxies around the local group versus the distances. This is McConaughey in 2012. And what you see here is the arousal of a beautiful isochrone. And this is a beautiful evidence, I think, a very strong evidence that the universe must have a finite age, right? This relation between the radial velocity, which is a perturbed Hubble flow, must necessarily tell you that this kind of model must be correct, at least something like this. Right, so the interesting bit now is that you can see here that our model is very simple, and yet it looks very much like the data. And the model is going to depend on these three quantities: the mass of the local group, h0, and omega lambda, and the age of the universe, of course, right? And you know that the age of the universe in lambda CDM is determined by h0 and omega lambda. So you see everything is fully specified. In principle, we should be able to fit this relation by knowing three parameters: the mass, h0, and omega lambda. Now, not everything is so simple. For example, you see here particle or galaxies, these are real galaxies, I'm sorry, that don't appear in this simple model. Here we don't find any particle. The isochrone is negative in that part of the diagram, and this is because these are the satellite galaxies. Again, this is very simple to the top hat spherical collapse model, where we are only following the first pericentric passage. Whereas the satellite galaxies around the Milky Way and 31 have been orbiting around us for many more years. But from here on, basically from 700 kiloparsecs from the local group center, what you see is that the Hubble flow becomes positive. These are galaxies that are still moving with the Hubble flow. They have never been within any of the galaxies of the local group, just because the initial velocities were probably very high. Anyway, so this is the model that we are going to use. Now, there is another difficulty in this model, which is that we are not sitting at the center of the local group, unfortunately. This introduces some geometry into the game, which is now the question is, where is the center of the local group, the barycenter of the local group in this case? To find the barycenter, what we did was something in principle, an approximation, which is the mass of the local group, the mass budget, is dominated by our galaxy and M31. So if that's the case, and if you can assume that, then the local group barycenter is going to be in between these two galaxies, necessarily, under that assumption. So at least we know that the location of the barycenter now is going to be fully determined by the mass ratio between our galaxy and M31, what we are going to call Fm. Now, the sun is not at the center of the Milky Way either. So you have to correct for that or include that. And we know the distance more or less is 8 kiloparsecs to the center. It doesn't really matter how precise we are because we are still working on megaparsec scale. So this uncertainty is fully negligible. But something that is very important is what is the velocity of the sun with respect to our galaxy, right? Because we are going to correct, we need to measure, we need to fit the velocities with respect to the local group. And for that, we need to know what is the heliocentric velocity. This is something we measure. And then we need to correct this heliocentric velocity by the solar motion with respect to the local group. This is what we call the solar apex. And the solar apex is determined by the velocity, the circular velocity of the sun at the solar radius, V0. This is around 220, 240 kilometers per second, plus the local standard of rest, the motion with the sun with respect to the circular velocity. And this is the motion of our galaxy with respect to the barycenter, which is fully specified by the relative velocity between the Milky Way and Andromeda and the mass ratio of these two galaxies. This is, again, something we measure from data. This is something we measure from data. We know where Andromeda is on the sky. So this is our free parameter F now. And we are going to also assume that this is a free parameter just for fun, because we are using a Bayesian analysis. So we want to know how the uncertainties in the solar motion, the circular solar motion around the Milky Way is going to impact on our measurement. So we allow this to be a free parameter, flat prior. We don't put any prior information. All right, so just to make you an illustration, how important is to know where the barycenter of the local group is. So this is real data now. So the only thing I'm doing is to calculate the velocities according to this formula, okay? And I'm going to plot them as a function of distance to the local group barycenter. And now the only thing I'm doing in this animation is changing the value of the mass ratio between our galaxy and M31. And this is what happens. How the data you are fitting changes when the mass ratio between our galaxy and Andromeda varies. So you see, it's interesting because you see that the scatter tends to increase when we assume mass ratios above 1. So, right? So you see here the scatter is very small, but as the mass ratio climbs about 1, then the scatter becomes quite large. So mass ratios above 1 in this case would mean the Milky Way being more massive than M31. So you can see already by eye, that it's probably the solution is going to be that the Milky Way is less massive than M31. That's the solution that is going to minimize the scatter in the observed relation. But we do this fully Bayesianly. That means including the uncertainties in our models. So we have this likelihood, it's just a Gaussian likelihood. We're assuming flat priors on all our parameters. We have parameters that appear in the equation of motion, the mass, h0 and omega lambda, again, flat priors. Let's assume that we know nothing about cosmology, only that the curvature of the universe is 0. Then we have parameters that appear in our coordinate transformation. That's the mass ratio between our galaxy and M31. This is the circular velocity of the sun in the Milky Way. And then we are going to use a hyperparameter, sigma. This hyperparameter turned out to be key. So for those of you that don't know what a hyperparameter is, it's something very close to a nuisance parameter. It's a parameter that you introduce in your model. It has no physical meaning, but you are going to fit on the parameter, and then you are going to marginalize over that parameter. And then, in other words, what these hyperparameters are used is to introduce uncertainties in your models that are not fully included in your models. For example, let me illustrate what I mean by that. So this is an animation of our very simplified model of the local group expansion. Here, the only thing I'm doing, every particle in the simulation is just some value, has some value for the initial velocity, and the only thing I'm doing is sampling the initial velocities. So you can see what I mean here by the contest between gravity and the local kinematic energies. You can see that some particles reach the turnaround radius and fall back, whereas others are still moving away from the local group. These are the ones with positive radial velocities. You can see the turnaround radius here very nicely. And in the end, you end up with very simplified isochron, right? It's a line, because we are assuming that all these trajectories are radial. And this is, of course, a bad assumption, because we know that there is going to be loads or sources that, in principle, they are going to introduce tangential motions around the local group. You have, first of all, systematic errors, which are going to be there, and we don't know. That's why, by definition, they are systematic. We cannot correct for these. They are going to be in the data. Then you have that some of these galaxies in the local group are actually pairs. They are orbiting around each other, and that means that they are going to inflate the observed Hubble flow. Then you have neighbors, right? In reality, the local group is surrounded by other groups with similar masses beyond 3 megaparsecs, and those perturbations from nearby groups also lead to some tangential peculiar motions, right? So what I did here was to some very, very simple experiment. I take the results from the simulation. I take 100 points from that simulation, and then I introduce a tangential motion, Gaussian errors with these magnitudes, very similar to observational ones. And then I am going to introduce some tangential velocity in random directions, and this is what happens to the Hubble flow. As you can see that these tangential motions basically inflate the relation. And the interesting bit is that when you introduce this hyperparameter here in quadrature, in the variance in your models, again, this is a free parameter to fit. This is what happens when you don't introduce the hyperparameter and when you do. And what you see is something very interesting that is really worth highlighting for the students here, is that if we assume that there is no hyperparameter, you can still get a fit to the data. The problem here is that the uncertainties, for example, for this particular realization, the uncertainties are not realistic. You end up with a very small error bar, if you want, on your parameters. Here will be the mass and the mass ratio. The uncertainties will be unrealistically small. You are still many sigma ways from the true solution, right? When you introduce a hyperparameter, what you're saying is there is systematic errors. There is another source in the scatter in your Hubble relation that is not just purely the observational errors, the errors in velocity and distance. There is something else that we don't know how to account for that. Our models will become extremely complicated if we try to introduce the peculiar motions. It's much better to introduce in a statistical way this uncertainty and then marginalize over sigmas. And then when you end up with error bars that are much larger, but now realistically large, at least all our models are now within 1 sigma of the true solution, which is what you want. All right, galaxy sample. We have these galaxies between, we take galaxies between 700 kiloparsecs and 3 megaparsecs. Beyond 3 megaparsecs, you start to see other groups. So these are not in our equation of motion. They are not included. They could be included, but we didn't. So this gives us 35 galaxies to which we can apply our equation of motion and get a fit. And this was the result. Just the posterior, the sampling of all the parameters. You see, basically, all parameters are well behaved. You get something like Gaussian posteriors. Basically, all of them. You get, for example, a local group mass of around 2 times 10 to the 12 solar masses. The mass ratio between the Milky Way and 31 is 0.5. So it seems that 31 might be twice as massive as the Milky Way. You get a measurement, incredibly enough, of the circular velocity of the sun around the Milky Way using galaxies that are megaparsecs away. And this is, well, similar. The error bars are large, but they are similar to what people find locally. And then the only thing that is interesting here that should be highlighted is the strong degeneracy between omega lambda and h naught, or the reduced h. This degeneracy, interesting enough, is it's almost running parallel to the age of the universe. So basically, we can measure the age of the universe, but not really break the degeneracy between omega lambda and h. So what we did here was to say, OK, let's now take omega lambda from the cosmic microwave background, because in lambda CDM, omega lambda should be constant. It's a constant. So we could sample now the posteriors of I think this was Planck. So this is sampling the Planck posteriors in our prior volume, and then you will get a measurement. You can see here that if you now say omega lambda must be in this range, you get a very well-defined value for h. And this is what we got. This is a value of h naught measured locally within 3 megaparsec. It's very close, actually, to the value that people get from supernova and from other sources in the literature. So which is telling you that, in principle, lambda CDM, this very, very simple, extremely simple description of a lambda CDM works very well on megaparsec scales. At least there is nothing weird. The only weird thing, and I'm sorry if I'm running a little bit late, was that the mass we get, around 2 times 10 to the 12, is a factor 2 smaller than what people were getting from the relative motion between M31 and the Milky Way, the classic timing argument that people found. You can see here in this diagram that all the galaxies we were fitting were following this kind of isochron, but if you plot the relative velocity and distance of M31 and Andromeda, they are much more negative. So this much more negative translates into a much higher mass. As you can see here, people did in 2014, they found again that for the age of the universe of 14 gigayears, and the relative motion of M31 in the Milky Way will give you something closer to 5 times 10 to the 12. But where is this discrepancy coming from? We are using exactly the same equation of motion. And the only difference here is that these guys are moving much faster than they should, at least. Or you explain how you can shift all these points to some direction, which is much harder. And here's where finally the LMC comes about. Because this is a picture we took from Paranal. You can see the LMC last year. Well, Dennis took it. I didn't. I was there, though. The LMC was here. SMC, you guys are beautiful. It's a beautiful picture. And the question is now, well, I was considering that the mass, so basically, to calculate the barycenter of the local group, I was assuming that the Milky Way barycenter sits at the center of the Milky Way. Is this a good assumption or not? So Facundo came to me and said, well, wait a second, because this is true if actually the LMC has very small mass. But it turns out that we don't really know what is the mass of the LMC very well. So people have got kinematics data all the way to 9 kiloparsec, and in the velocity is flat, and 9 kiloparsec is around 70, 80 kilometers per second. So a very simple formula like this would tell you that the mass enclosed within 9 kiloparsecs is of the order of 2 times 10 to the 10 solar masses. And this is the number that people have been using in the literature for many years, for decades. The game changed a bit when HST measured the proper motions of the LMC. And what they found is that an astonishing number. They found that even though the LMC is located at 50 kiloparsecs from the Milky Way, it's moving at 370 kilometers per second away from our galaxy. This is a very, very large number. Actually, you take now this proper motion from HST and integrate back all these orbits, assuming that the Milky Way has something like 10 to the 12 solar masses, which is similar to what we get. Then you get that the LMC must be falling in for the first time. And if the LMC is falling in for the first time, then it might be surrounded by a large dark matter envelope, as you would expect in lambda CDM. And if that's the case, well, then the 9 kiloparsec mass is only the mass enclosed within that radius. The total mass of the LMC could be much larger. How much larger is what we try to figure out. So if you don't know anything about the total mass of the LMC, at least you can say, well, what is what people find in simulations, for example, using abundance matching? If you go to these simulations, for example, these ones, what people do is very simple. They rank dark matter halos by mass, and then they rank galaxies by luminosities and say the most massive one must be the most luminous one. Then they get a relation for mass of the halo versus mass of the inner stars in those halos. That looks like this. So for the luminosity of the LMC, which is something like 3 times 10 to the 9 solar luminosities, you would expect a virial mass of the order of 3 times 10 to the 11 solar masses. This is the virial mass you would get for an isolated halo, or a halo that is falling in for the first time. This is a very high mass, as you can imagine. 3 times 10 to the 11 is almost 10 times larger than the mass enclosed within the region where we have data. Now there is a second argument that points toward a massive LMC, which is that HST also measures the proper motions of the SMC. And then you can say, what is the relative velocity, 3D velocity now, between the LMC and the SMC? And it's very high. It's 130 kilometers, 130 kilometers per second. Again, if you want both systems to be gravitationally bound now, because it would be very weird if they come from separate directions and we happen to find them now close to each other, that would be extremely unlikely. So if they are now gravitationally bound, these authors show that the total mass of these two objects has to be above 10 to the 11 solar masses. So it's another argument in favor of a massive LMC. So what we did was very simple. I said, okay, let's assume that we don't know the total mass of the LMC. Well, how would that change the mass of the local group that people get from the timing argument? It's a very simple calculation. You take this equation of motion, again, appears everywhere. You say the N31 and the distance is now 870 kiloparsecs from measurements. The relative velocity between N31 and our galaxy can be calculated simply like that. Again, this is a measurement. And the only thing that we need to include is now the mass ratio between the LMC and our galaxy, what we call FC. This is what HST was measuring, 370 kilometers per second. You see already what is the interesting feature here is that even if the LMC mass is very small, the relative velocity is so large that it can have an impact on the relative velocity that we would infer from N31 and our galaxy. So the classical timing argument can be, in principle, very sensitive to the unknown mass of the LMC, and you can see it here. This is the mass of the local group. Again, if you assume that the LMC mass is negligible, you get something like 5, 10 to the 12th. If you now increase the LMC mass, you see that this number is going down and down. And it's going down to the point of a mass of the order of 2.8, 10 to the 12th, if the LMC mass is higher than 2.5, 10 to the 11 solar masses. So you can halve the mass of the local group just if the LMC is massive. But you cannot measure the mass of the LMC here. It's completely degenerated. What we see is that the mass of the local group and the mass of the LMC are degenerated quantities. So, okay, so it's a little bit more complicated, but now we can repeat the analysis we did before, including the LMC. And now the apex becomes a little bit more messy. Again, this is 300 kilometers per second. You have now the mass ratio between M31 and our galaxy, and the mass ratio between LMC and our galaxy. So you repeat exactly the same analysis, the same data sets, and this is what you find. And this is interesting. Here is if you pay attention, here is the log of the mass ratio between LMC mass and our galaxy versus the local group mass. You see, the mass of the local group doesn't really depend much on the mass of the LMC you get when you feed the Hubble flow, okay? This is the analysis when we feed the 35 galaxies between 1 and 3 megaparsecs. So that mass that we get doesn't change, doesn't barely depend on the LMC mass. We see that the LMC mass that is high ratios are preferred, but it's still a strong degeneracy. As you can see, the posterior distribution still has a very long tail. Now you can do is say, okay, now I want to fit the local group, the perturbed local group, and the perturbed Hubble flow around the local group, and the relative motion between M31 and the Milky Way simultaneously. And if you do that, because now this is pointing really to a low local group mass, what you end up is that you remove all these possible solutions where the LMC has a small mass, and you end up with a preferred mass for the LMC that is pretty high. Sorry? It's 1/5. Yeah, I'll show you in a second. So the mass of the LMC that we get is around 2 times 2.5, 10 to the 12. The mass we get for the Milky Way is 10 to the 12. So if you add them, so m a fourth if you divide by another. Yes, or a fifth if you add the total mass of our galaxy. Yeah. Sí. Exacto. And this is clearly pointing that for this to be true, because we were not assuming anything about the LMC, it was just a free parameter. Yes.
How we should understand that this is the mass of the LMC today?
Yes. So it's the mass of the LMC today. I'll show you a video in a second where, because it's falling in for the first time, after doing this, we thought, this is crazy. We cannot, this is probably because we are assuming the point mass things. And when we correct here, this is basically a conservation of angular momentum analysis where you assume that it's a point mass and all that. So it's a very simple way of accounting for the presence of the LMC. It's the simplest one. So what we did was to run live embodied simulations where the Milky Way and the LMC were live systems. And those simulations were run by Dennis. We were ending up with models where the LMC is located at the right location with the right velocity. And then we repeated our analysis. It works very well. Within 5%, we were recovering the true values.
So this means that this is the first passage?
Yeah, only in the first passage. Yes, exactly. Yes, the first passage. And it's being stripped. The thing is that we happen to find the LMC right at pericenter, where the tides are still compressive, and most of the mass is still around the LMC. If you wait, you would see that the formation of tidal streams and all that. But we happen to find it at right almost close right at pericenter, I think 15 mega years after pericenter. So yes, it's a very high mass. Again, even here we get the mass of the Milky Way and M31 grow a little bit, but this is still very close to 10 to the 12. The M31 is still slightly more massive, apparently. But it's interesting that with this method, you can fit simultaneously the masses of 3 galaxies, the total masses of 3 galaxies, right? The mass of LMC, M31, and the Milky Way in one go, which is, I think, is a positive thing. Right, so this was the results early this year. As I said, we didn't particularly believe this result very much. We thought, well, this is what you get if you adopt the timing argument and then you repeat all this analysis, these cosmological arguments. But then, in order to confirm or to falsify, you would really have to go to the LMC, measure kinematics, and try to see whether there is evidence for an extended dark matter distribution in this galaxy. A few months later, after our letter got published, these 2 guys in Cambridge analyzed the DES data, trying to find substructure in the stellar halo of the LMC here. So this is the northern galactic cap. You see the Sagittarius stream. the southern galactic cap, again, the continuation of the Sagittarius stream. LMC is here, and the dense footprint only covered half or 1/4 of the LMC, as you can see here. So what these two guys found was this. Around the LMC, they found tidal streams. So a stellar stream, which in principle looks like it's orbiting around the LMC, we still need to go and measure kinematics. But the interesting bit is that the apocenter of this stream, they could measure distances, the relative distance between the LMC and these stars over here, and it was above 50 kiloparsecs. Mind you, the distance of the LMC to the Milky Way is 50 kiloparsecs, right? So if this galaxy, if the LMC had been orbiting many, many gigayears, many orbital periods around our galaxy, all these features would have been stripped away. So the fact that you see tidal streams at distances that are larger to the galactocentric distance of the LMC is, I think, a very strong evidence that the dark matter halo of the LMC could be much more extended than this, right? And again, it's pointing toward first passage. Otherwise, it would be. Not only that, a few months later, this is moving very, very fast now. A few months later, after these two authors discovered the tidal streams around the LMC, these people, again, with Vasily as collaborator, this is a student, and Dennis, my collaborator, basically they went to all these new ultra-faint dwarf galaxies that people have discovered in the DES data. And for many of them, I think there are 14 new dwarf stellar galaxies here in this sample. And it's been very fast because people immediately went to telescopes and measured the velocities of these tiny objects. And then they say, well, are these velocities and locations, because we can know now the relative distance to LMC and the relative velocities, are they compatible with being ultra-faints of the LMC, right? That come together with the LMC, as you would expect in lambda CDM. If there is an extended dark matter envelope, these galaxies should have their own satellites. So they are satellites of satellites in this case. And what they find is that at least within 2 sigma, at least half of these galaxies might belong to the LMC. So the LMC might be bringing actually quite a lot of the ultra-faint dwarf galaxy population of the Milky Way, because if you take now these numbers, say of the 15, 7 belong to the LMC within 2 sigma, and this is 1/4 of the LMC halo, how many could be in total? And what they find is of the order of 70 galaxies. The LMC might be bringing of the order of 70 satellite galaxies to the Milky Way. This is, again, a very exciting and very interesting discovery. The last thing I'm going to show is this plot, because it's been too long, and I apologize. Is that actually, if you have the LMC being as massive as these numbers that we are getting, and then unfortunately our galaxy is not in equilibrium anymore, because now you have a galaxy LMC at 50 kiloparsecs with a mass of the order of 2 times 10 to 11 solar masses, and the mass of the Milky Way within 50 kiloparsecs is 3 times 10 to 11 solar masses. So right now, our galaxy has a very similar amount of mass within the radius where the LMC is located. And this is a very, very non-equilibrium configuration and can have some important impact on the stellar tracers of our galaxy. This is, for example, a work by Facundo. This is the orbit of Sagittarius, of some model of Sagittarius, looking at the angle between the orbital plane of Sagittarius versus time, how this changes. So because there is a disk, you see there is some basically precession of the orbital plane of Sagittarius dwarf. But when the crossing of the Milky Way, of the LMC, when the LMC crossed the Milky Way virial radius 0.7 gigayears ago, it's moving really fast. So it's less than 1 gigayear ago, the LMC was not within the Milky Way. So it's moving in, and we happen to find it at pericenter. And you see here the difference in the orbit of Sagittarius. It changes dramatically. And this has very interesting, very strong implications, if this is really correct, on the potential of the Milky Way that people were trying to derive, the mass of the Milky Way that people were trying to derive, using the stellar tracers that I was showing you in the second slide of my talk. So this is, again, a very interesting, potentially very important effect that the LMC could have on our understanding of our galaxy. So this is just a very quick summary of what we found. using these cosmological arguments, the timing argument, basically this modeling of the Hubble expansion within the local group, we find that the LMC must be quite massive. Might represent a fifth or a quarter, depending on how you define the ratio of the Milky Way mass. And this number that we get, 2.5 10 to the 11 solar masses, is almost exactly on top of the abundance matching constraints that you would expect from those simulations, which is, we didn't expect that, and I don't know whether it's a miracle, is the right word to use, but it seems to work well. Yes, it's the scenario that only makes sense if the LMC is falling in for the first time, and as other people have been arguing in the past. And the LMC and SMC would be bound with this mass. This has interesting implications, especially for people that are trying to understand how galaxy formation in low mass halos. Now you have a large population of satellite galaxies in the Milky Way that might have been formed in the LMC, not in our galaxy. So this will be satellite galaxies that in principle might have different properties just because they form in a different galaxy. It has implications for all these people modeling the Milky Way potential, especially in the era of Gaia. This might be an interesting thing to follow up. And yeah, for people also trying to find local group analogs, they were using this old number of 5 times 10 to the 12 solar masses, which is only true if the LMC has a negligible mass, which is not the case, at least in these models. And with this, I'm finishing, and thanks very much for your attention, and sorry if I'm
Very interesting. Yeah, I agree that the number of here, the Milky Way similar galaxies in the Sloan, for example, sample shows that the galaxies that have 2 satellites like LMC and SMC are very, very rare in the local universe. And so this is, I think, interesting, your results confirming in some sense this, that is a very strange case. I have a question regarding your model. In your motion equation, you have the term of acceleration, the term that have the lambda. I think that this term should be very, very, very small. Yeah. So, because you are obtaining omega lambda 0.7 and the Hubble parameter more or less as observed. So it's curious that all your statistics having this very, very small term can give you results that are
no, it's rather that basically the way the omega lambda appears in our, sorry, one more, no, here. It's basically because omega lambda and h naught appear in the definition of the age of the universe. That's the main effect. There is an effect at 3 megaparsecs. These terms I think introduces a 30 kilometers per second difference in the Hubble flow. But at 3 megaparsecs, the Hubble flow is already of the order of 250 kilometers per second. So you are right. Yeah. Here the effect is of the order of 10% or smaller. But here the effect is very important if you want to derive the right age of the universe. So if you set omega lambda here equals 0, then you get the age of the universe wrong. Or
including M33 in a similar analysis may perturb the conclusions or maybe constrain even better? Okay, you are prepared, bro.
You were the referee, probably?
No.
No? Let me see whether I can find this without jumping too much. Yes, it's a very small effect. No, there are proper motions for M33 as well. It's just the geometry, I think, is playing a very small effect. You can see here, this would be where the blue line is when we neglect the M33, and then the dashed line is when we introduce the proper motion of 33, and then assume, say, the barycenter of M31 might not be located at the center of M31, and repeat the analysis similarly, and the effect is small.
Pues está muy padre todo el esquemita. Las masas tan altas que salen para el LMC simplemente se me hace que no cuadran. Y yo creo que ahí lo que está fallando es otra de las hipótesis, que es que la velocidad inicial sea puramente radial, sobre todo entre Andrómeda y nosotros. O sea, yo creo que hay una velocidad tangencial entre Andrómeda y nosotros, y creo que esa puede ser la hipótesis que esté requiriendo estas masas que a mí me parecen un poquito infladas para el LMC. Y creo que un argumento en favor de velocidades tangenciales entre el Milky Way y Andrómeda tiene que ver con estos, por ejemplo, el hecho de que son dos discos que están girando en sentidos opuestos y que haya sido un tidal torques entre los dos los que dieron origen o sea, sabemos que hay un tidal field que te da un spin en sentidos opuestos para estos ambas galaxias grandotas, o sea, y eso no lo puedes sacar si pones velocidades puramente radiales entre ambas.
No, we are not putting velocity. We are fully using the 3D velocity of 31.
Okay.
So these are, sorry, you cannot see very well. These are 3D vectors.
Okay.
So we are using the proper motions and the radial velocities on 31.
Pero está suponiendo que originalmente la velocidad era puramente radial, ¿no?
And this is part of the hyperparameter business that I was mentioning before. It's true that the equation of motion, this equation of motion are fully radial, but then introducing the hyperparameter is what allows us to correct for the tangent. There is...
To correct?
Maybe, yes, it's true. But we have basically what I'm doing now, and I didn't want to talk about this, is using simulations to test our method, right? And what we're finding is that this is, for example, 12 apostle simulations. This is the mass ratios, our parameter FM versus the virial mass of the simulations. And what you see, basically, using this hyperparameter and the full 3 motion and all that, the same analysis. It's only that here we fix the cosmology. Then we see a very small bias in most of the cases. I think there is one apostolic 12 that has a very uncertainties that are not representative of the deviations. But for the rest, it looks quite good. But yeah, this is work in progress, so we are trying to understand whether there could be some bias in our analysis. It's true, it's very simple. You cannot model the local expansion more easily than this.
Okay.
I would like to know a bit more about the mass-to-light ratio that you derive from this dynamic derivation. Well, this derivation of the total mass. Does that fit with what the people said? Because you saw a velocity curve of that does predict a lower dynamical mass.
No, actually it agrees too well, I would say, because I never believed in this abundance matching. This is what people do. They go and measure the stellar mass to light ratio as you want, or basically it's not the mass to light ratio, it's the stellar mass versus halo mass. You can divide one by another and you will get the mass ratio. But what you see is that the mass we get, which is 2.5 10 to the 11, is basically what you would expect from this cosmological simulation. So it agrees too well with this simple.
Okay, so the luminosity for your mass, the luminosity should be of the 9.5 in logarithmic scale, something like the stellar mass, I mean.
The stellar mass is 3.3 times 10 to the 9 solar masses.
Okay.
Yeah.
That was my point.
Could you repeat a bit more about what is the argument for the tidals in LMC? Because it's already known that LMC has wide tidals.
Interesting. So, okay, yes. So it's true that there's a stream associated to LMC, but in gas. The people have tried to find tidal streams in stars, and for many years, and they never found it. They only see a gas stream which actually is located on the sky, on locations that you would not expect from the HST proper motions. It seems that the gas is here, but the orbit is going somewhere else. So people never understood what was going on with the gas. And I think the current models from Cortina Besla showed that if the LMC and SMC have been interacting, as you would expect from the relative motion derived from HST, that would heat up the gas and then induce some ram stripping. When the LMC and MSNC are falling through the virial radius of our galaxy, then ram stripping of the gas could have taken place. This is the current understanding in how we can understand the formation of a gas stream without a stellar stream. For the stellar stream, what we found is this is the simulations I was talking about. Again, here I'm only showing the Milky Way disk. And there is a dark matter halo, a live dark matter halo I'm not showing. And this is the LMC. And this is the simulations I was talking about at the ends in the right location, right velocity. This is what happens. So even though these two galaxies are live, you see, and there is some deformation due to the tidal stripping, most of the mass is still around the barycenter of, around the maximum density of the LMC. So it seems that not even the halo has been stripped very much, and the stars are still living within the Dana halo, with it being mostly undisturbed by the tidal field. But this is only first info-less scenario. So yes, to strip the gas, you need something else, like this ram stripping and the interaction with the SMC, maybe.
But you also mentioned something about ultra-faint dwarfs.
Yes.
And what about globular clusters?
Very good. Nobody has looked at that. It's interesting. Yeah, we know that the LMC comes with many globular clusters. Most of them tend to be metal-rich, so they are mostly located around, or distributed around the stars of the LMC. So in the same volume, these 9 kiloparsecs. But I don't think people have looked for, as ultra-faints like globular clusters. I would say that most of the problem there might be that we don't know the radar velocities for many of those distant clusters, might be. I don't know, but I don't know anything about that. It's a good point.
¿Otra pregunta? ¿No? Una pregunta mía. Pero han estudiado cuál sería el efecto. Es que una cosa de ese tamaño ya es casi como interacción de galaxias. ¿Han estudiado qué le pasa al disco de la Milky Way? Porque a mí lo que me preocupa un poco es qué pasa con los fine-tuning stuff, ¿no? Como la química, que es muy suave, que con una cosa de ese tamaño yo creo que esto ya estaría todo revuelto, ¿no?
It's true. There are people looking at the dynamical effect. I don't think there is anyone looking at the star formation history. Remember, the interesting thing about this scenario is that the LMC crossed the virial radius of our galaxy 0.7 gigayears ago. Sorry?
Very recent.
Very recently, so this is 3 or 4 orbital periods for the disk, and it's right now at pericenter. So most of the effects, if you are looking for effects of the LMC on the Milky Way disk, you probably must look at the young generation of stars, right?
I see, exactly. But
Exactly. The ones that were born after the LMC was crossed the Milky Way, and then compare that with the old populations and see whether there is an obvious difference. There are people looking into the dynamics of that, but I don't know whether anyone is looking into the star formation.
Okay.
I bet that there will be some warp, for example. Could be some indication there, some effects.
Okay.
Interesting effects. And all these monoceros stream, whether it's a ring or is some material being ejected from the disk. It's going to be very interesting this opens up a number of interesting questions in general.
It's just kind of scary.
It was my first reaction, when I saw the mass that we were getting, I said, well, this is very scary if true, because
Porque ya no puedes predecir nada con la barra, los brazos, así tranquilamente, porque esta cosa va a desarmar todo esto que es secular, que de veras toma mucho tiempo y resulta que una cosa de estas ¡pras! Destruye todo lo que predijeron.
It might help to solve other problems that people were not able to solve in the past. No?
Okay.
It's a challenge and an opportunity.
Way to see. Okay. Espero que estés equivocado.
Lo bueno es que no me pagan por eso. Está equivocado, ¿no? Bueno. Sí.
Porque entonces